theoretical overview of the perceptron and how to build a neural network from a group of perceptrons, we're actually going to learn how to implement a neural network with R using the neural network package or library for R. Let's go ahead and jump to RStudio to get started. Okay, here we are at RStudio. We got some pretty cool stuff in store for this lecture, but before we begin, we have to actually get our data. In this case, we're going to use the famous or popular Boston dataset, and it's from the mass package with R. And if you don't have the mass package, all you need to do is go to your console, and just like in the notebook, it says you can put in install.packages and capital MASS, and that should give you the mass package. Once you have the mass package installed and downloaded, you can just call it library mass, and you should be able to call the head of capital BOS Boston. Let me go ahead and expand the console and script for a little bit and hit enter here. And you'll see we have a bunch of features of houses in Boston. Keep in mind this housing data is from a publication that's from 1978, so it's pretty old, but it'll do for what we're actually trying to do. In this case, each of these columns represents some sort of feature of a house. For instance, this CRIM is the per capita crime rate per town. Then we have this RM, which is the average number of rooms per dwelling in that particular area of Boston. You have the tax rate, the ages of the housing, etc. At the very end, we have this median value of owner-occupied homes in the thousands of dollars. What we're going to be trying to do is essentially almost like a regression problem where we have a bunch of features and we're going to try to predict a continuous value, which is the median value of owner-occupied homes in the thousands of dollars. If you want more information on what each of these columns actually represents, check out the notebook where there's a description of each of the features of this data frame. Let's check out how large the data frame is by calling structure. Remember, that's str, pass in Boston. And it looks like we have 506 observations and there's 14 variables, meaning the 13 features, and at number 14 we have what we're trying to predict, which is the median value. Let's go ahead and just quickly check to make sure we don't have any missing data. Remember, the way we check for missing data, I'm going to clear the console, is by saying any is.na, and then you pass in your data. In this case, I'm just going to pass in that Boston. And we get false, which means false, there is no NA values in Boston, meaning we're not missing any information. So that's all great. Let's go ahead and clear the console, make a variable data, and assign Boston to it. That way we can mess around with data, and it's a little more clear than just typing Boston all the time. We won't do any exploratory data analysis in this lecture, but in your project that's coming after this lecture, you will do a little bit of exploratory data analysis on a data set you haven't seen before. For now, we're going to focus on actually training a neural net model. In order to do this, we need to do two things. We need to pre-process our data, and then you actually need to install the neural net library. Let's continue on the data path and actually pre-process our data. Whenever you're training a neural network, it's a good practice to normalize your data. And we can use the scale function in order to normalize our data. Depending on your data set, avoiding normalization may lead to useless results or to a very difficult training process, meaning a lot of times the algorithm won't converge before the number of maximum iterations is allowed. But you can choose different methods to scale your data, such as a min-max scale, z-normalization, a bunch of different statistical methods for scaling and normalizing your data. What I'm going to do is teach you how you can customize your arguments in the scale function in R. In the upcoming project, I'll just have you use the default arguments for scale, and that means it's going to be a lot more straightforward. But I do want you to know how you can actually customize the arguments that we put into our scale function. What we're going to do first is grab the min and max values of each of the columns in our data frame. And we're going to do that using apply. I'm going to create a variable called maxes. And I'm going to call the apply function. I'm going to apply over my data, and I'm going to add a second argument called margin. And if you want more information on what that second argument margin does, you can just call help on apply, and it should take you to the documentation, apply functions over array margins. But basically what's going to happen is if you just put in a 2, it indicates that we want to apply this over the columns. And that's exactly what we want because I want the maximum value of each of the columns, which is why I'm going to pass in a 2 here as my margin argument. And then I'm going to pass in a function that I want to apply over the columns. And in this case, the function I want to apply is max. Let's go ahead and see that. And now let's check out maxes. Notice now I get the maximum value for each of the columns, meaning the maximum value for the median value of a group of houses is $50,000. We're going to do the same thing for the minimum values. Let's go ahead and say in argument mins. Make sure you have an S at the end of maxes or mins that we don't overwrite the actual max or min built-in functions. We're going to apply over our data, that's the Boston data set, put in 2 because we want to do this over the columns, and then put in min for the minimum function. And now let's go ahead and check mins, and now we have the minimum values for each of the columns. Now what I'm going to do is use these mins and max values in order to scale my data or normalize my data. Let me go ahead and clear the console. And what I want you to do is go ahead and call help on the scale function. And it should take you to a page that looks like this in the documentation. You'll notice that scale is just a generic function whose default method centers and or scales the columns of a numeric matrix. And that tells you 2 things. 1, that it has default arguments, and 2, it's going to return a numeric matrix, meaning we'll have to transform it back into a data frame. Notice that these other arguments, center and scale, can be either logical values or numeric vectors. In your project, you're just going to leave them as the default logical values, but right now I'm going to show you how you can actually pass in the min and max values we just calculated in order to customize your normalization. What the first center argument is, if we're going to pass in a numeric vector for center, then each column of our data has the corresponding value from center subtracted from it. Meaning I'm going to do this. I'm going to call scale on my data and say center is equal to mins. And that means each single data point in the column is going to have the minimum value subtracted from it. And then we have the second argument, which is scale. And if we pass in a numeric vector for scale, each value in our data set is going to be divided by the scale. And that means I want the scale to be maxes minus mins. All I'm doing right now is I'm saying get my data, and in every data point subtract the minimum value of that column that it's in, and then divide it by the maximum value minus the minimum value. And that's going to normalize my data. Let me go ahead and set this equal to scaled data. I'm going to push over the documentation so we have a little more room here. And now I have my scaled data, but remember this is a matrix, and that means I want to actually say scaled or scale.data and pass it in as a data frame. I'm going to say as.dataframe and pass in that matrix. And then I can get back head of scaled, and I'll notice everything's been scaled now or normalized. And that's exactly how we want it for a neural net. This is a really important step, and you should always make sure you're normalizing your data whenever you're working with a neural net. Otherwise, you'll get funky results or it just won't converge. I'm going to push this a little more to the right so we have a little more room to work with. And if you want to confirm that this is actually scaled, you can just go ahead and check out the head of the built-in Boston data frame. And notice that we actually have different values here. You can even just check here in the median value, notice that everything's now between 0 and 1. Versus in the original, you actually had the real values. Now that we've standardized our data, let's go ahead and split it into a training set and a testing set. Now we're already really familiar with this process. Hopefully you can just do this on your own by now, since we've done it for basically every lecture and every project. But remember, you just call CA tools, get a variable split, call samples.split, and then our scaled data, pass in any column. I always like passing in what we're trying to predict. In that case, it's the median value. And our split ratio is just going to be 0.7. That means we'll have 70% of the data be for training, which means I will say train is a subset of scaled where the split is equal to true I'll just put in capital T. And then test is the subset where scaled split is equal to false. Let's go ahead and run that. It looks like everything's good. We get a warning message, but again, that just has to do with what version the library is built on. But if I go ahead and say head of train, looks like everything's working out. Let me go ahead and clear the console. Now we're ready to actually train our model. We're going to need the neural net package in order to do this. And that means if you don't have it yet, go ahead and in your console, say install that packages, and in quotes, pass in as one word neural net. Once you've done that, you should be able to call library neural net and have it all come out for you. All right, now that that's installed, let's go ahead and actually use the neural net function from the neural net library to train a neural network. For some odd reasons, this neural net function won't accept the formula in the classic form that we're used to, where we just say y and then tilde and dot. It doesn't accept that form. For whatever reason, you have to actually manually put in col1, column2, etc. Usually we're used to being able to avoid that process by just using the dot, but this time we're actually going to have to manually put those all in. I'm going to go ahead and show you a little trick that will help you avoid that manual labor of having to type all those out. Go ahead and ask for the names of the training data set, the column names. That means when we call n, we see all the column names. And in your notebook, you have a piece of code. I'm going to go ahead and copy and paste it from the notebook now. You grab it, copy, paste. And what this does is it automatically joins all of these column names together into a formula. Let me go ahead and just quickly break this down. What we're doing is we're just grabbing every single column name, pasting it together with a plus in between, and then at the very beginning we're saying MEDV for the median value, tilde, and then we're going to go ahead and paste in as long as it's not in MEDV, and then casting it as .formula. And that's going to save you some time just using this names function and then using this formula little cheat code that I put in the notebook for you. And then when you call F, you'll see that this formula actually has already been written out for you. And that way you can avoid the process of having to manually type out each of these column names. Hopefully that's useful to you, but that's what you're going to have to do since you can't use the dot notation for the neural net function. Let me go ahead and clear the console now and actually train our neural net. I'm going to create a variable called nn, call the neural net function. It takes in a formula. Again, we couldn't do something like this. We have to type in the whole formula. In this case, I already saved it as f, so I'm just going to put in f. I'm just going to train on my training data. Then the second argument is that data. And then we have an argument called hidden. And what the hidden argument does, it's a vector of integers specifying the number of hidden neurons in each layer. Go ahead and check out the Wikipedia articles as far as maybe what are reasonable values to choose here. But I'm going to go ahead and just choose a first hidden layer of 5 neurons and a second hidden layer of 3 neurons. You could keep adding to this, but for right now we'll just leave it at that. And then since we're not doing classification, we're actually doing some sort of continuous value. What we're going to go ahead and say is our final argument, linear.output, equals true. And you would set this to false if you're actually performing a classification problem for your neural net. But let's go ahead and now train our neural net. Okay, and what's really cool here is we're actually going to be able to plot out the neural net that we just created. Let me go ahead and show you how you can do that. I'm going to expand the visualization window a little bit. I'll put it all the way out so we can clear that linear output nicely. All right. And then all you have to do is say plot and pass in the variable that is your neural net. And you will see the plot of your neural net. Let's go ahead and zoom in on it. And this is one of the good things and nice things about a neural net. Basically, a neural net, you're going to have to treat it a bit of a black box because it's really hard to interpret what each of these actual weighted vectors really means in reference to the column values of your data. We can see here that the black lines show the connections between each layer and the weights on each connection. And these blue lines that we see show the bias term added in each step. Again, the bias can be thought almost as the intercept of a linear model. The net here is essentially a black box. That means we cannot say that much about the fitting, the weights, or even the model. What we can say is that this training algorithm converged, and therefore the model is ready to be used on some sort of testing data. All right, let's go ahead and move on to actually creating predictions with our model. Again, I hope you thought this visualization was pretty cool, even if it's not super interpretable. I'm going to go ahead and close that, push it over to the right, and it's time for some predictions. I'll just go ahead and do this all in the console. I'm going to make a variable called predicted NN values. And for the neural net function, you just use the compute function. And you use compute instead of predict like we're usually used to. You pass in your neural net model, and then you pass in your test data without the labels for it. And that means columns 1 through 13. Remember, there were 14 variables or features in that column data frame. We just want the first 13 of them because we don't want that actual label. And then we compute those values. If we check out the structure of what came out of that, this predicted NN values, notice we get back a list of two. There's neurons and there's the net result. What we actually want is the net result. But remember, we scaled and normalized our data for the training model. What we have to do is basically undo those operations in order to get the true predictions. And that means I'm going to make a variable called true predictions and say predicted NN values net result. And I'm going to go ahead and just copy this formula from the notebook and then quickly explain it. Remember that we were subtracting from the center value and then dividing by that scale value when we performed our normalization operation. And basically here we're just inverting that. Notice that I'm saying instead of dividing by max minus min of that median value of our data, I'm saying multiply it by the max minus the min, and then instead of subtracting from that center value, I'm saying go ahead and add that center value. And I'm just grabbing the max and min from that specific median value column. And this will essentially unscale or get non-scaled predictions. Let me go ahead and also convert the test data. I'm going to go ahead and just copy those. I'm going to say test.r and basically doing the exact same thing. And the reason I'm doing that is in order to actually get some sort of mean squared error from this. I'm going to say mean squared error, or MSE, and say NN. Remember, that's the sum of our test minus our true predictions. And the reason I called it true, whoops, that should be a minus sign, is because these are the non-scaled predictions. And then what I'm going to go ahead and do is square this, and then we divide it by the number of rows in our test set. And that's the mean squared error. We can go ahead and call it now and figure out the mean squared error. What we can also do is visualize this error in ggplot2 by actually just graphically showing the true predictions plotted by the test values. All right, let's go ahead and create a data frame called error_df, and I will call the data frame function and pass in my test values. I'm going to call them test.r, and then my true unscaled predictions. Let me go ahead and check the head of that error.df. All right, and this is basically what we have. We have the test value for that particular house. This was row 2, row 4. Notice these aren't sequential because we did that random train test split. And then we have these true predictions. These are the unscaled predictions of our neural net. Looks like we're not doing too bad, but let's go ahead and visualize this by saying the test values on the y-axis and the true predictions on the x-axis. I'm going to call, let me go ahead and clear the console here. I'm going to call ggplot2, which we're already very familiar with. Say ggplot error df, pass in our data. And as the aesthetics, I'm going to go ahead and say x is the test r, and y is those true predictions. I want this to be a scatter plot. I'm going to go ahead and say geom underscore points. And then I also want to go ahead and put in a stat smooth line, just to see a little more on the visual side how we did. Let's go ahead and run that. Whoops, and that should have been stat smooth, not state smooth. Let's pull this plot out. And there it is. Let's go ahead and click zoom. Remember that a perfect prediction would just basically be a straight linear line with a slope of 1. And here is our true predictions, meaning our unscaled prediction values, versus the actual test data. Looks like there were some houses that threw off our model, but overall it's not looking too bad, especially considering all we had to do was normalize our data, and we treated the neural net as essentially just a total black box. And that means we can conclude a couple things. That neural networks resemble black boxes a lot. Explaining their actual outcome and how they interpret the features is much more difficult than explaining the outcome of a simpler model, such as like a linear regression. Therefore, depending on the kind of application you need, you may want to take this into account as well. That means if you're doing something at work or your own project where you need to specifically interpret the importance of each of the variables, a neural network that is a little more black boxy may not be as good as a simpler model. And then furthermore, as you've seen here, extra care is needed to fit a neural network in order to actually use the data. And that means stuff like normalization of your data. Okay, I hope you enjoyed this lecture. Coming up next is your neural network project. Thanks everyone, and I'll see you at the next lecture.